Hi everyone and welcome to this course on Python for beginners. In today's AI-driven world, Python stands out as the ideal language for beginners due to its simplicity and powerful libraries. This course takes you a hands-on journey through essential Python concepts, core machine learning, deep learning, and natural language processing. You will build real AI models, write and run the code, and gain practical skills to confidently start creating AI application. Whether for a new career upskilling or even a personal interest, this course is for you. So, are you ready to unlock the power of AI with Python? Let's get started. Here's a roadmap of what we will cover. We will begin with Module 1, which is building a solid foundation by understanding the core concept of artificial intelligence and why Python is the language of choice for this field. In Module 2 and 3, we will dive into the essential tools and theoretical underpinnings, first exploring the crucial Python libraries like and Pandas, and then moving into fundamentals of machine learning, including supervised and unsupervised learning. Module 4 is where we get practical. We'll apply our knowledge by implementing machine learning models hands-on using the powerful library. In Module 5 and 6, we will elevate our understanding by introducing neural networks and then exploring deep learning, specifically focusing on its application in image classification and convolution neural network. In Module 7, we will introduce you to fascinating world of natural language processing, covering its basics and key application. And right after Module 7 will be a dedicated practical session where you will get to build a CNN from scratch, bringing concepts of deep learning to life. By the end of this session, you will have a clear understanding of AI and ML fundamental, practical experience with key libraries, and solid grasp of how approach both traditional and deep learning tasks. So let's get started. In our first comprehensive module, Introduction to AI and Python, we'll lay foundation bricks. We will begin by defining what artificial intelligence truly is and why Python stands out as a language of choice for AI development. Then we will get hands-on by guiding you through setting up your Python environment and introducing you to powerful interactive tools like Jupyter Notebooks and Google Colab. Finally, we'll reinforce your core Python skills, focusing on syntax and data structure vital for AI programming. Let's get started by defining our core topic, artificial intelligence. In the essence of AI is about enabling machines to stimulate human intelligence. This means empowering computers to perform tasks that typically require human cognitive abilities. Our key goal in AI include enabling machines to reason and solve problems, learn and improve from data without explicitly being programmed, and perceive and interpret their environment, and also understand human language to interact naturally. Think of everyday examples like self-driving cars, navigating complex roads, voice assistants like Siri or Google Assistants, understanding your commands, or even the personalized recommendations you get on Netflix or Amazon, all powered by AI. Now that Python language of choice is AI, especially for beginners, now why is Python language the choice for AI, especially for beginners? First, Python's simplicity and readability make it incredibly easy to learn and write code, which is crucial when you're just starting out. Secondly, it boasts vast ecosystem of specialized libraries and frameworks specially designed for AI and machine learning, which we'll explore shortly. This means you don't have to build everything from scratch. Thirdly, there is incredibly large and active community around Python providing immense support, resources, and collaborative opportunities. Lastly, Python is platform independent, meaning your code will run seamlessly across different operating systems like Windows, Mac OS, or even, and its versatility extends beyond AI to areas like web development and data science, making it a valuable skill overall. For AI development, particularly for beginners, Jupyter Notebooks are incredibly popular. They provide an interactive web-based environment where you can combine live code, explanatory text, and visualizations. This makes them perfect for experimentation, data exploration, and presenting your work. Even more cloud-based accessible is Google. This is a cloud-based service that offers free access to Jupyter notebooks, including powerful GPUs and TPUs for faster computationals as well as a local setup. It is also excellent for collaboration. The key advantage of both of these tools is their support for iterative development, allowing you to run the code in small chunks and see immediate results. Before we dive into coding, we need to set up our workspace. The first step is to install Python, preferably Python, which you can download directly from the official Python org website. Once installed, Python comes with pip. It's packaged installer which we use extensively to manage our AI libraries. The best practice is to use a virtual environment. These are crucial because they allow you to create isolated environments for each project, preventing conflicts between different library versions. I have included a basic commands to create a virtual environment. First, you will need integrated development environment, which is an IDE. Popular choices for Python development include Visual Studio Code and PyCharm, offering features like code completion and debugging. Let's quickly review some fundamental Python syntax and data structures essential for AI. You will work extensively with variables and data types like integers, floating point numbers, and you will also use various operators for calculation and comparison. Control flow statements are crucial for dictating how your program executes. This includes if statements for making decisions, for loops for iterating overall collections of data, and loops for repeating actions until a certain condition is met. Finally, functions are your building blocks for creating reusable code, helping you organize your programs and avoid repetition. Beyond basic data types, Python offers powerful data structures that are foundation for handling data AI. Lists are ordered and mutable, meaning you can change their contents after creation, making them versatile for storing sequence of data. Are similar but immutable, often used for fixed collection of items. Dictionaries are incredibly important for storing data in key-value pairs, allowing for quick retrieval based on unique keys. Think of them as a real-world dictionary where a word is the key and its definition is the value. Lastly, sets store unique, unordered elements useful for operations like finding common item or removing duplicates from a collection. In Module 2, Essential Python Libraries for AI will introduce the powerhouse of Python AI ecosystem. We'll delve into NumPy for high-performance numerical computing, which is the backbone of many AI operations. Then we'll explore Pandas, an indispensable tool for data manipulation and analysis. Finally, we'll learn the effective visualize our data using Matplotlib and Seaborn, gaining insights that are crucial for understanding and communicating our AI projects. Our journey into AI libraries begins with NumPy, short for numerical Python. Its core contribution is the ND array, which is powerful n-dimensional array object. Why NumPy is so crucial for AI? Because it provides incredible efficient numerical operation on large data sets, far outperforming standard Python lists. This efficiency is critical when dealing with massive amounts of data in AI. In fact, NumPy forms the foundation for many other AI libraries, meaning that a solid understanding of NumPy will benefit you across your AI development. Let's look at how we work with NumPy arrays. You can create arrays from existing Python lists or generate arrays filled with zeros, ones, or even random numbers using functions like np.zeros, np.random.rand. A key feature of NumPy is the ability to perform element-wise operation, meaning arithmetic operation like addition or multiplication applied to each corresponding elements in an array. You can also efficiently index and slice arrays to access specific elements or subsets of data. Finally, understanding the shape of your array, its dimension, how to reshape it as a fundamental for manipulating data in various AI tasks. Next up, we have Pandas, the Python data analysis library. While NumPy is great for numerical operations. Panda excels at handling and manipulating structured data. Its two core data structures are the series, which is like one-dimensional labeled array, and the data frame, which is two-dimensional tabular data structure resembling a spreadsheet or a SQL table. Pandas is indispensable for AI because it allows you to load data from various sources, clean the messy data sets, and transform the data into right format, handling missing values, and even merge different data sets. It's the go-to library for preparing your data for machine learning models. Let's delve into the working with Pandas data frames. You can create data frames from various sources including Python dictionaries, lists, or even most commonly by loading data from a CSV files using pd.read CSV. Once you have a data frame, you can perform numerous operations. Selection allows you to access specific columns or rows. Filtering lets you subset your database on certain conditions, for example, selecting all entities where a value is greater than 10. You can also group data by categories and apply aggregate functions and sort your data based on specific columns. A crucial aspect of data preprocessing is handling missing data, and Pandas provides convenient methods like drop na to remove rows with missing values or fill na to replace them. Finally, for understanding and communicating your data, we have Matplotlib and Seaborn. Matplotlib is a foundation plotting library in Python, allowing you to create a wide range of static, interactive, and even animated visualizations. It gives you fine-grained control over every aspect of your plot. Seaborn, on the other hand, is built on the top of Matplot and provides higher level interface specifically for statistical graphics. It often makes it easier to create aesthetically pleasing and complex visualization for fewer lines of code. Why is visualization so important in AI? Because it helps us understand data patterns, identify outliers, or even unusual data points, discover relationship between variables, and most importantly, communicate our insights effectively to others. In the next module 3, which is Machine Learning Fundamentals, dives into the heart of AI. We'll start with core concepts of machine learning, what it means for machines to learn from data. We'll then differentiate between supervised and unsupervised learning, understanding when and how to apply each. We'll explore fundamental regression algorithms like linear regression and classification algorithms like logistic regression, which are building blocks for many AI applications. Finally, we'll cover essential model evaluation metrics, learning how to assess our model's performance accurately. Now we move into exciting world of machine learning. At its heart, machine learning is about teaching computers to learn data without being explicitly programmed for every single task. The core idea is that by analyzing vast amounts of training data, a machine learning algorithm can identify underlying patterns and relationships. Once trained, this model can be used to make predictions or decisions on new, unseen data, a process referred to as inference. Machine learning broadly falls under two main categories: supervised learning and unsupervised learning. In supervised learning, our model learns from labeled data, meaning each input data comes with a corresponding correct output. The goal is to predict an output based on new input. It further breaks down into regression, where we predict a continuous value like house price, and classification, where we predict a category, such as whether an email is spam or not. Some examples under supervised learning are spam detection and house price prediction. On the other hand, unsupervised learning deals with unlabeled data. Here the goal isn't to predict a specific output, but rather to discover hidden patterns or inheritance structures within the data. There are two categories in unsupervised. First one is clustering, similar customer together, and second one is dimensionality reduction to simplify complex dataset. Examples include customer segmentation and anomaly detection. Let's dive into our first type of supervised learning algorithms. Regression is used when we need to predict continuous numerical value. A fundamental regression algorithm is a linear regression. The algorithm models the relationship between your input features and continuous output target by finding the best fit, which is a straight line through the data. The simple equation y is equal to mx plus b represents this, where y is the predicted output, x is the input, and m is the slope, and b is intercept. Linear regression is commonly used for tasks like predicting stock prices, forecasting sales figures, or estimating future temperatures. Next, we have classification algorithms, which are used to predict categorical label or a widely used classification algorithm, despite its name, is logistic regression. Don't let the regression part confuse you. It's powerful classification technique. Instead of directly predicting a continuous value, it predicts the probability that an input belongs to a certain class. It achieves this by using sigmoid function to squash the output into a value between 0 and 1, which can be interpreted as a probability. Logistic regression is ideal for tasks like spam detection, disease diagnosis, or even a simple image classification. Let's explore decision, which are highly intuitive and visually explainable algorithms. Imagine them as a flowchart-like structure, where each internal node represents a test on an attribute to or feature. Each branch represents an outcome of that test, leading to further tests or ultimately to the leaf node, which provides the final prediction, either a class label for classification tasks or a numerical value for regression tasks. Their main advantage is being easily to understand and interpret, and they can handle both numerical and categorical data. However, a drawback is that they can easily overfit the training data, meaning they might not generalize well to a new unseen data, and they can be sensitive to small variations in the dataset. Next, we have k-nearest neighbors, or KNN, as a straightforward yet powerful algorithm. It's considered a non-parametric and lazy learner because it does not build an explicit model during the training phase. Instead, when you want to make prediction for a new data point, KNN simply calculates the distance between these new points and all existing training points. It then selects the k nearest neighbors, which is k for the number you choose. For classification, it assigns a new data point to the class that is most frequently among its k neighbors. For regression, it would assign the average value of the k neighbors. KNN is appealing for its simplicity, but it can be computationally expensive for large dataset as it needs to calculate distance to all points. And it's also sensitive to irrelevant features and scale for your data. Building on decision tree, we have random forest, an extremely popular and powerful ensemble learning method used for both classification and regression. Instead of building just one decision tree, random forest constructs an entire forest of many individual decision trees. Each of these trees is trained on a random subset of the training data, and for each split, it only considers a random subset of the features. For classification, the final prediction is determined by the majority from all the individual trees. For regression, it's the average of their prediction. The main advantage of random forest are its high accuracy. It's robust to overfitting and its ability to handle missing values and provide insights into the feature importance. The trade-off is that it becomes less interpretable than a single simple decision tree due to the sheer number of trees involved. Finally, let's look at support vector machines, or SVMs, another powerful supervised learning algorithm. For classification, the core idea is an SVM is to find the optimal hyperplane that best separates data points into different classes. This hyperplane is chosen such as it maximizes the margin, which the distance between the hyperplane and the closest data point from each class. These data points are called support vectors. One of SVM's most innovative feature is the kernel trick, which allows it to handle non-linear data by implicitly mapping it into higher dimensional space where it can be linearly separated. Are effectively high in dimensional spaces, are memory efficient, and are versatile due to the various kernel functions. However, they can be very slow for a large data set and sensitive to the scaling of your features. After training machine learning models, it's crucial to evaluate its performances to understand how well it generates the new unseen data. We use various matrices for this one. One of them being confusion matrix. A confusion matrix is a table that provides a comprehensive view of a classification model's performance by breaking down its predictions into four core values. These values are true positive, which is TP, representing instances where the model correctly predicted the positive classes. Negatives, which is TN, where it correctly predicted the negative class. False positive, which is FP, and false negative, and false negatives were incorrectly predicted the negative class. To calculate various performance metrics like accuracy, precision, recall, or F1 score, you simply take these four values directly from the confusion matrix and substitute them into relevant formulas. Accuracy is more straightforward, representing proportion of correct predictions out of all predictions made. However, for imbalanced data sets, accuracy can be misleading. That's where and recall come in. Precision tells us out of all the instances our model predicted as positive, how many were actually positive. Recall, on the other hand, tells us out of all the actual positive instances, how many did our model correctly identify? Finally, F1 score is the harmonic mean of and recall, providing a single metric that balances both. It is important to remember that the choice of the metric depends heavily on specific problem you're trying to solve. In Module 4, we'll be seeing how to implement ML models with Scikit-learn. We'll be discussing building and evaluating a linear regression model as well as a logistic regression model. Along with that, we'll be also learning about data preprocessing, scaling, and normalization techniques to make your model perform its best. So for building and evaluating a linear regression model, first let's import the essential libraries. We'll bring in NumPy for numerical operation, especially when working with arrays. And then we are importing Pandas to help us handle and manipulate our data in a structured way. And then we are also importing Scikit-learn as mentioned earlier. Now, after implementing all the modules that require, we'll move on to data generation. Let's create a simple synthetic data so we can see linear regression in action. X here represents our input feature. We are generating 100 random numbers between 0 and 10. Y is our target variable. We are making it dependent on X with a bit of random noise added to real world data. So let's execute these both. The next step is very important, splitting our data. We divide our data into training sets, that is what the model learns from, and testing set, what we use to evaluate the model or unseen data. We'll be using 80% of the training data and 20% for testing, which is the random state, just ensures the split is consistent every time we run this. Let's just divide the data according to 80/20 rule. Let's quickly see the shape of our training data. So the shape is 80/1 and 80/1. Now for next step, we are going to do model initialization and training. Here we can create an instance of our linear regression model where we are importing model is equal to linear regression. This is the core step, the fit method. This is where our model learns from the training data, figuring out the best line to represent the relationship between X train and Y train. So let's run this. So this is also done, and now that we have done with the model fitting, now it's time to make predictions. So we have y predict is equal to model.predict x state. This tells us how well our model performs on our data. Next we have model evaluation, where we have to judge if the model is performing up to the mark or not. So for that, we are using mean squared error, which is MSE, and also R square. So we have mean squared error as 3.74 and R squared as 0.93. A value closer to 1 means a module explains more of a variation and is generally better. Next, let me show you how visualization of predictions is done. Let's visualize our prediction helps us intuitively understand our model's performance. We'll import Matplotlib for plotting. We'll also plot the actual values of our test as blue dots. Then we'll draw a line that our model predicted in red and give our chart a clear title. So as you can see, this is the visualization graph, and we have given target and feature as the commodities and the title as linear regression, where linear regression actual versus predicted is the title. Now we are moving on to building and evaluating a logistic regression model. Again, we are starting by importing our necessary libraries. This is our logistic regression model from classification, which is also a package. And there are specific matrices we'll use to evaluate our classification model, such as recall, F-score, and confusion matrix. That is also mentioned here. And also the utility helps us create sample dataset for classification. So let's import all these libraries first. Now, after this, the next step is definitely to generate the data. So for demonstration, we are generating a synthetic dataset perfect for binary classification, meaning 2 distinct categories. We'll create 100 samples with 2 informative features, which is X and Y. And just like that, before we split the data into training and testing sets, which is our next step. Again, here also we have given random state as 42, and the size is also 0.2, which is 80% in the training and 20% in the testing. Next, we move on to model initialization and training. So definitely we have model is equal to logistic regression, and we are fitting the entire data set. Finally, we are making predictions. With the trained models, we use predict to get the predicted class of labels, which is 0 or 1 for our test data. And the predict prob method gives you the probability of each test sample belonging to each class. So let's see how the model has performed using accuracy, precision, recall, F1 score, and confusion matrix. So here are the results. Accuracy is 1, which won't be true most of the time for a real-time data. Now we have precision is 1, recall as 1, F1 score, and confusion matrix between 13007. Next, we have some plotting to be done, which is visualization. This gives us a more clear picture of your data. So firstly, for 2D data, we can visualize the decision boundary. Our logistic regression model learned. This helps us see how the model separates different classes. These are just some colors on the maps of our plots, which is /FFA. These are representation of colors. We create a mesh to plot the decision boundary, which is h is equal to 0.2. We predict the class for each point in the mesh. And then this plot the background colors based on our model's prediction, showing the decision region. And rest is just giving the numerical representation and the title, the X and Y labels. So let's run this and see this visualization. So as you can see, this is the logistic regression line, and the segregation is too perfect in this case, which is unreal for a real-time data. Now let's see how data preprocessing, which is scaling and normalization, is done. So as usual, firstly importing the libraries required for the function and also loading of the data. These are the 2 major steps that will be repeated in every kind of problem that you're solving. So here we are creating a sample data. So feature 1 has much larger data set than feature 2. This difference in scale is exactly what we are scaling addresses. Then we have imported standard scaling, which is standard scaling transforms our data so that each feature has a mean of 0 and standard deviation of 1. In min-max scaling, also known as normalization, transforms our data due to specific range, typically between 0 and 1. This often preferred for algorithms like neural network that expects into features within a bounded range. Similar to standard scalar, fit.transform finds the minimum and the maximum values in our data and then scales at all values up to 0 to 1 ranges based on those min or max. So let's run this also, and there is an error. So let's rectify this error. It says that the name scale data min max is not given. Okay, we have not fit the model. There is a code missing. So I have fixed that scale data min max and we have fit it to a transformer df. Now let's run it and see the results. So as you can see, the same feature 1 and feature 2 have been scaled up where the values is easily scalable and also plottable. Welcome to Module 5, which is Introduction to Neural Network. In this module, we'll be exploring practical part from building and evaluating a linear regression and logistic regression model, data preprocessing, specific scaling, and normalization. And we will also be covering model selection and hyperparameter tuning. So let's get started. Let's start with the very basics of neural networks. Fundamentally, they are computational models inspired by structure and function of the human brain. Think of them as being composed of interconnected neurons or nodes, which are organized into distinct layers: an input layer, one or more hidden layers, and an output layer. The learning in neural network happens by adjusting the strength of the connections between these neurons, known as weights, and by modifying these biases, small offsets that give neurons flexibility. When a neural network has substantial number of these hidden layers, we refer it to as a deep learning, allowing it to learn incredibly intricate and abstract pattern in data. To grasp how neural network process information, let's visualize its architecture. It always begins with the input layer, where your raw data, where its number of images or text is fed into the network. Following this one is one or more hidden layers. These are workhorses of the network. They perform complex computational progressively, extracting and transforming features from the input data. Finally, the output layer produces the network's ultimate prediction or classification. Information flows between these layers through connections, each having an associated weight that determines the strength of the signal passed from one neuron to the next. Crucially, activation functions are applied within the neurons to introduce non-linearity, which is absolutely essential for the network to learn and more complex real-world relationships that aren't simple linear. Now let's see what activation function is. An activation function introduces non-linearity into a neural network, allowing it to learn complex patterns and relationships in data beyond simple linear transformations. Activation functions are vital for a neural network's ability to learn complex patterns. Their primary role is to introduce non-linearity into the network. Without them, even a deep neural network would simply be performing a series of linear operations, limiting its power to model complex data. We'll look into three common ones. The sigmoid function squashes its output to range between 0 and 1. Historically, it was popular for hidden layers, but now it's often used in the output layer for binary classification tasks where you need a probability. However, it can suffer from vanishing gradient problem during training. Value or rectified linear unit is defined as a maximum of 0 and x. It's currently the most popular choice for hidden layers due to its computational efficiency and the ability to help mitigate the vanishing gradient problem. Next is the tanh, or hyperbolic tangent, squashes its output to range between -1 and 1. It's often used as an alternative to sigmoid for hidden layers, as its zero-centered output can sometimes help with training stability. TensorFlow, developed by Google, is a comprehensive open-source machine learning platform. It's powerful, highly flexible, and allows a low-level control, making it excellent for large-scale and complex research. Whereas Keras is a high-level application programming interface, or an API, designed specifically for building and training neural networks quickly and easily. It's incredibly user-friendly and can run on top of TensorFlow. The relationship is that Keras simplifies TensorFlow. It provides a more intuitive and modular way of defining neural network architectures, making deep learning much more accessible, especially for beginners. Together, they form a powerful duo of building, training, and deploying of neural networks. Let's outline the practical steps for building a simple neural network using Keras user-friendly sequential API. First, you will import Keras from TensorFlow. Then you will define your model using keras.sequential. This means you're building a network layer by layer in sequence. Next, you add layer to your model. The most common type in Keras is keras.layers.dense, which represents a fully connected layer where every neuron in the previous layer connects to every neuron in the current layer. You will specify the number of neurons and activation function for each layer. After defining the architecture, you compile the model. This is where you configure the learning process by specifying three key things. The optimizer, which is how the network adjusts its weights during training, and the loss of function, what the network tries to minimize, that is the error, and then the metrics you want to monitor during the training, like accuracy. With the model compiler, you then train the model, the fit method, providing your training data. The number of epochs, that is how many times the network sees the entire dataset, and the batch size. Finally, after that training, you will evaluate your training model on unseen test data to assess its performance, typically using the same matrices defined during compilation. Understanding the training process is fundamental for neural networks. An epoch refers to one complete pass through the entire training dataset. If you have 1000 data points and train for 10 epochs, the network sees all 1000 points 10 times. Batch size determines how many samples are processed before the model weights are updated. Smaller batch update weights more frequently, while larger batches provide a more stable gradient estimate. The optimizer is the algorithm that intelligently guides how the model updates its internal weights and bias to minimize the chosen loss function. Popular optimizers include Adam and Sophisticate. Popular optimizers include Adam and stochastic gradient descent. The loss function is a mathematical formula that qualifies how far you and your model's predictions are far away from the true values. For example, mean squared error is used for regression and categorical cross entropy for classification. The optimizer's goal is to minimize the loss. For evaluation during training, it's crucial to monitor the loss and metric on separate validation set. This helps ensure the model isn't just memorizing the training data, which is overfitting, but it's genuinely learning to generalize. The final evaluation should always be performed on a complete unseen test set to get an unbiased assessment of the model's true performance on a new data. In Module 6, we'll delve into deep learning for image classification, a field where deep learning has achieved incredible breakthroughs. We'll start by explaining convolution neural networks or CNN, the specialized architecture behind modern image recognition. We'll then get practical by knowing how to build CNNs using Keras. We'll also cover essential techniques for creating robust image models such as data augmentation and transfer learning, and discuss how to effectively evaluate the performance of image classification models. Convolution neural networks, which are CNNs, are a groundbreaking type of neural network specially designed for processing image and other spatial data. Their key innovation is their ability to automatically learn hierarchical features directly from images without requiring manual feature engineering. The convolution layer is the core component. It applies learnable filters that scan the images to detect local patterns like edges, textures, or specific shapes. Pooling layer then reduces the spatial dimension of the feature maps generated by convolution layers. This helps make the network more robust to small shifts or distortion in the input image and reduces computational load. Finally, after several convolution and pooling layers, The learned features are fed into fully connected layers, which is FC, which operate like a standard neural network to perform the ultimate classification based on extracted features. CNNs have truly revolutionized computer vision tasks, enabling machines to achieve superhuman performance in areas like image recognition, object detection, and facial recognition. Building a CNN with Keras is quite straightforward, especially using its sequential API. A typical CNN architecture in Keras follows common patterns. You will start one with core convo 2D layers. These are convolutional layers that apply filters to create feature maps from your image data. You will specify the number of filters, filler size, and activation function. Often max pooling 2D layers. These are pooling layers that perform downsampling, reducing, and spatial dimensional of the feature maps, which helps in reducing complexity and making the model more robust. After the convolution and pooling stages, you will typically use flattened layer. This layer converts the 2D feature maps into 1D vector, preparing the data to be fed into fully connected layers. Finally, you will add one more dense fully connected layer for a final classification. The last dense layer will have neurons equal to number of classes you want to predict with an appropriate activation function. Remember that the input shape parameter is very important for your very first Convo 2D layer, as it needs to know the dimension, which is the height, width of the channel of your input images. Data augmentation is highly effective technique, especially when you have limited number of training images. Its main purpose is to expand your datasets by creating a new, slightly modified version of your existing images. This helps your model to see more variations of the same object, which in turn significantly improves its generalization ability and prevents overfitting. Common techniques include flipping images horizontally or vertically, rotating images by small degrees, zooming in and out of images, and shifting images horizontally or vertically. Adjusting brightness or is also there. Keras provides a very convenient image data generator class that simplifies applying these augmentations on a fly during training. The ultimate benefit is more robust model that can be better handle variation in real world images and achieves higher accuracy on unseen data. Transfer learning is a powerful concept in deep learning that involves reusing pre-trained model that has already learned to perform a similar task, typically on a very large and diverse dataset like ImageNet, which contains millions of images across 1,000 categories. The core idea in these pre-trained models have already learned general low-level features like edges, textures, and common shapes in their early layers. And these features are highly useful across many different image classification. The typical process for transfer learning involves loading a pre-trained CNN architecture along with its learned weights, freezing the convolution base of this pre-trained model. This means preventing its original learned weights from being updated during training, preserving the general feature extraction capabilities. Third one will be adding new custom top layers on the top of a frozen convolutional base. These new layers will be specifically trained for a new targeted classification task. And finally, you will train only these new custom layers on your specific dataset. This requires much less data and computational resources compared to training an entire CNN from scratch. The immense benefits are that you need less data, training is significantly faster, and you can often achieve more higher accuracy than if you want. The immense benefits are that you need less data, training is significantly faster, and you can often achieve much higher accuracy than if you were to train a brand new model from scratch on your limited dataset. When evaluating image classification models, simply looking at overall accuracy might not tell the whole story, especially if you have an imbalanced dataset or specific concerns about false positive versus false negative. The confusion matrix is an invaluable tool. It's table that gives you detailed breakdown of your model's prediction versus the actual labels. It helps you to see exactly where your model is making mistakes. For example, if it's consistently confusing cats with small dogs. Per class metrics like precision, recall, and F1 score should be calculated for each individual category. This gives you much more granular understanding of how well your model performs on each specific class rather than just one overall average. For binary classification tasks, the ROC curve, which is the receive operating characteristic, and AUC, which is area under the curve, are important. The ROC curve plots the true positive rate against the false positive rate at various threshold settings, while AUC provides a single scalar value representing the model's ability to distinguish between the classes. Finally, don't underestimate the power of visual inspection. Manually looking at some of the images your model misclassified can provide invaluable qualitative insights into the weakness and guide further improvements. In our final module, we are exploring natural language processing, which is NLP, a fascinating field dedicated to enabling computers to understand and interact with human language. We'll start by understanding the complexity of bridging the gap between human language and machine understanding. Then we'll dive into key text processing techniques that convert raw text into machine-readable format. Next, we'll cover the text vectorization methods that transform words into numerical representation, which is essential for machine learning algorithms. Finally, we'll get a glimpse into advanced concepts like word embeddings, which are crucial for capturing the semantic meaning and relationship between the words. Natural language processing, which is NLP, is a field where we teach machines to understand and process human language. The ultimate goal of NLP is to bridge the communication gap between human beings and computers, allowing for more natural and intuitive interactions. NLP tackles a wide array of fascinating tasks, including text classification, such as automatically detecting spam emails or categorizing news articles. Sentiment analysis, which determines the emotional tone of text, whether it's negative or neutral, often used for analyzing customer reviews. Machine translation, like Google Translate, converting text from one language to another. Powering conversation AI like chatbots and voice assistants. However, working with human language presents unique challenges. Language is fully ambiguity. Words can have multiple meanings depending on context, and there are endless variation in slang, grammar, and phrasing that machines need to navigate. Just like numerical data or image, text needs preprocessing to convert it from its raw, unstructured form into a format that machine learning models can understand and process effectively. Tokenization is a fundamental step. It involves breaking down a continuous stream of text into smaller, meaningful units called tokens, which are typically individual words or sentences. For example, I love NLP might become I space love space NLP and then a exclamatory mark. Stop word removal is another common technique. Stop words are very common but often less informative. Words in the language like the, is, and removing them can reduce noise and improve efficiency for many NLP tasks. Other important pre-processing techniques include lowercasing all the text to treat. The and the with capital T and a small t are the same word, and stemming or lemmatization to reduce words in their base or root form. Example, running, runs, ran, all become run. Since machine learning model inherited operate on numerical data, we need to vectorize text, which means converting our words into text. The bag of word BOW model is simply widely used technique for this. It represents a piece of text as collected or bag of words ignoring grammar and word order. Essentially, it counts how many times each word appears in a document. While simply it has limitation, it can give too much weight to very common words like the or a. This is where TF-IDF, which is term frequency inverse document frequency, comes in. TF-IDF assigns a weight to each word that can reflect its importance not only within a specific document but also across the entire collection of documents. It reduces the impact of common words that appear everywhere and gives higher scores to words that are frequently in a specific document but rare across the entire dataset, making them more distinctive and informative. One of the most practical and widely applied areas of NLP is sentiment analysis. This involves determining the emotional tone or polarity of a piece of text, whether it expresses positive, negative, or sentiment. The typical process involves collecting and labeling data such as movie reviews, tweets, or customer feedback. The labeling can be manual or semi automated. Then you can pre-process the text using techniques we just discussed, converting it into numerical format suitable for machine learning. Next, you can train classification model like logistic regression or SVM or even a simple neural network on the vectorized labeled data. The model learns to associate word patterns with specific sentiments. Finally, you will evaluate the model using standard classification matrices to ensure its performance well on unseen text. Sentiment analysis has a wide-ranging applications from understanding public opinion on social media, analyzing customer reviews to improve products and services, to monitoring brand reputation online. A major limitation of bag of words and TF-IDF is that they don't capture semantic meaning or relationship between the words. For example, king and queen are related, but in BOW and TF-IDF wouldn't inherit know that. This is where the problem that word embeddings solve. Word embeddings are dense vector representations of the word where each word is mapped into a point in multi-dimensional space. The core idea is that words with similar meaning or appear in a similar context will have similar vector representations and thus be close to each other in the space. Two prominent algorithms for generating word embeddings are word-to-vector. This model learns embeddings by predicting the context of word. It has two main architecture. One is continuous bag of words, which is CBOW, which predicts a word given in its context, and skipgram, which predicts context given a word. Second, we have GLOVE, which is global vectors for word representation. GLOVE combines aspects of global matrix factorization and local context windows to learn its representations. The immense benefit of word embeddings is their ability to truly capture semantic and syntactic relationships between words, leading to significantly better performance in advanced NLP tasks by providing models with richer understanding of languages. So let's see how to build and train a CNN. Starting with importing all the necessary libraries like TensorFlow, Keras, NumPy, and Matplotlib. Then we'll move on to loading the dataset. First, we'll load a standard image dataset, which is CIFAR10, which I've used here, directly from Keras. It's a collection of small color images divided into 10 categories. So let me just run the import section and load the dataset. And once that is done, the next vital pre-processing step is normalizing the pixel values. Images typically have pixel values from 0 to 255. We scale them down between 0 to 1. This helps our neural networks train more effectively. So for normalizing them, we use divided by 255. So that is also done. Next, we have to define class names for plotting. So class names I've given as aeroplane, automobile, bird, cat, deer, dog, frog, and horse, ship, truck. So let's execute this as well. That is also done. Let's quickly visualize a few sample images from the dataset. So we'll get to see some sample images. So this is the desized images where the pixel size will be from 0 to 1. So as you can see, truck and horse, bird, frog, and bird are given. Next, now let's build our convolutional neural network. So this is the model where CNN model is equal to model.sequential, which I've already explained. First, a convolution layer, which is con2D. This layer applies filters to detect features like edges or textures. We simplify 32 filters totally with 3x3 and ReLU activation. Input shape is very crucial. Very first layer matching our 32 by 32 pixel RGB, which will be 32 3,3. Next layer will be max pooling layer, which of 2D. This reduces the image dimensions and then helping to reduce complexity to make the model robust to small shifts in features, which is 2x2. We add another set of Convo 2D max pooling layers to learn more complex features and one more set for even deeper feature extraction. So totally we have added about 3 neural network layers. After the convolution layer, we flatten the output. This converts our 2D feature maps into 1D vector, preparing them for final fully connected. Now, fully connected dense layer, these are like traditional neural networks. The first one has 64 neurons with ReLU activation, and as well as the second one has 10 neurons with softmax which is CIFAR. Softmax activation. Softmax activation ensures the output's probability to sum up to 1. Then this is for compilation. We compile our CNN. We use Adam optimizer sparse category cross trophy as loss because our labels are integers and accuracy as our metric. CNN model.compile and the optimizer is being mentioned. Let's see the summary of our CNN architecture. So here you can see the summary of our CNN architecture. Now we have to train the model. So for training, this will take a few moments as it's processed. The image will train about 10 epochs. So this will take a little bit time. So we are running 10 epochs, meaning it sees the entire data set 10 times. So as you can see, we have just executed and it took about 30 minutes to execute the 10 epochs. So next, after training, we evaluate our CNN on the test set to see final performance. So since that is done, we have acquired the test accuracy as 0.73. Now on an optional basis, we can plot the training history. So there are a few things that I have plotted from the training validation accuracy, and there is a subplot of training and validation loss and also some of the predictions. So here you can see prediction for the first 5 test images. We have actually cat and the model predicted as cat, but here as you can see there are few misfortunes also which you will be able to see here. So this is how you train a CNN model. So that was it on this course of AI Python for beginners. Thank you so much for watching.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.